Okay, so this is for strengths, and this is week 5 quiz. So it's the quiz that we took, well, I don't remember the dates, maybe like the 18th or 19th, 18th, I think the 18th of September. And a lot of you all are like, you're really struggling with the quizzes, and many of you aren't completing it. So I just thought I'd work a couple of quizzes and let you go through them. So the first thing is there are a number of these, which symbol, come on, focus, focus, there we go, which symbol or which equation. So we need to remember that normal stress we call P over A, but it's really that internal normal force. And if I'm looking at stretching, it is causing elongation. Okay, sigma. When I'm looking at shear, it's going to be that V over A, and we are looking at deformation that changes this angle gamma. Okay, so you need to understand that normal means perpendicular to the surface and shear means parallel. If I put a parallel like force on top of this and went oink, like a brake on my bicycle. Okay, so if you're confused on these equations, please come and see me or see a TA. Okay, ultimate stress. So ultimate stress is the ultimate it can take. When I have this lower curve and the upper curve, notice that I have values here and values here for strain. If I look at these top numbers, they go with the top curve. And you can see the elastic region is super tiny. I couldn't read those numbers. If I couldn't even pull off a strain if I wanted to. But because we had it's such a ductile material, we have lots and lots of yielding before we have fracture. I have to use this upper scale so that I can see the full chart. Okay? If I want to look at just this elastic region before we hit yielding, then I need to make a much smaller scale, a much smaller scale, so that I can actually see what's happening. So when I look at this, okay, I'm getting the full spectrum of my testing all the way to fracture. When I look at this, my scale is so much far smaller, I would have to like continue on and on and on and on and on and on, and then tape some paper together and then tape more together, and I would have a super ginormous, longer than our room piece of paper to show the entire yielding at this much, I mean, look at that, smaller scale. Like, that's a huge difference, okay? So if I want the ultimate stress, it's right up here at the top. Okay, ultimate, and that's 150 to 180, so I know that this has to be 165, and we're kind of like here in the middle, so I'm just going to say that my ultimate is 157. And I have a range on these types of numbers where I probably said like 156 to, I don't know, maybe 160, something like that. It should be in that ballpark. But if you come back, you can see it's about halfway between 150 and 165. So ballpark about 157, 158. That's my ultimate. Stress, ultimate. Okay? Next problem. If the displacement at point C is 2.44 inches, what is the change in this length? Well, change in length is delta. It is length final minus length initial. But it is ultimately delta. So this is deformation. We're looking at deformation, so I can draw my little, okay. So if I know that I have a displacement here of 2.44 inches, I'm also going to have a delta of my cable from B to D. I don't really care anything else about materials or anything. I'm just looking at deformation. And I can see that this is 5 times 9.2, and this is 3 times 9.2, but really I can divide out the 9.2, and it's a 5 and a 3. So I'm going to have 5 is to delta BD as 5 plus 3 is to 2.44. And I'm going to cross multiply, and I get my delta of BD is going to be, so I have 5, 2.44 times 8 divided by, and it should be smaller because smaller part of the triangle, 1.525 inches. Okay, So this right here is 1.525 inches. And all I wanted to know was the change in length. And I know that change in length is just delta. I didn't ask for the final length. I didn't ask for the strain. Just what is the change in length? Okay, so that's my solution. And then it says to the hundredths place, so 1.53 inches would be my total delta. A bar has a length of 9.1 inches. So I have a length initial of 9.1 inches. I have a cross-sectional area of 13.3 inches squared. I want to determine the modulus of elasticity, that's E, if the material is subjected to an axial load of 10.26 kips and stretches, okay, so my delta, it stretches 0.004 inches. Okay, we are linear elastic, so that means I can use Hooke's law. So, enter as a whole number with units, my modulus. So I know that stress is P over A. That's from chapter 1. And I know that stress is related to strain. That was chapter 3. I also know that strain is change in length over length. This was chapter 2. So I can put this together. P. I have a load of 10.26 kips divided by an area of 13.3. Delta. I have a change in length of 0.004 inches. I had an initial length of 9.1 inches. So I can plug that there, and calculate E. So 10.26, 13.3 divided by strain. 0.004 enter, 9.1 divided by, and then we multiply by the reciprocal. So here's my reciprocal, and I multiply, and I get 1755. And it says in KSI, and I've been working in kips and inches. So there's my answer for that problem. It's just understanding what the definitions are. If I say the change in length, I have to know that change in length means delta. Okay? I have to know that a load is P. And I have to know how stress and strain are related. And now we actually could put it all together, and we know that delta equals PL over AE. And if I rewrote this, I would find that E equals P over A, length over delta, which is what I found here because I had to multiply by the reciprocal. Okay. Let's see what the next problem says. What is the yield force? So force means I'm in units of kips or newtons or pounds, okay, or kilonewtons force. If the cross-sectional area is, okay, so we're in inches, so that means I'm looking at kips or pounds for my unit of force, 10.65 inches squared. So the yield force has to come from the yield stress. And the yield stress is roughly right here. Okay, that's where I go from elastic to plastic, all the way across. If this is 90 and this is 120, then this has to be 105. That's right in the middle. Okay, so if stress is P over A, and I have 105 KSI equals P over 10.65, then the load that causes yielding, my yielding load is just 105 times 10.65, and I get P equals 1118.25 kips. Keep up with my units. And answer to the whole number. So 1118. Determine the magnitude of the shear at the pin at A. Okay, so shear, okay, is V over A. Enter if P is 1719. And I know that my lengths are 70 and 49. This doesn't really matter. Who cares about the cable? Irrelevant. Okay? So the shear is going to be my reaction at A. It's going to be the square root of the x component and the y component, because we end up with an x and we end up with a y. But actually, the resultant, okay, we're actually pulling back in the direction that is the combination of x and y. So I need to find ax, I need to find ay, then I can take the magnitude, okay, and that's how I would design a shear pin. So let's sum forces in the x direction equals 0, and I'm going to have ax minus 1719 times 3/5 equals 0. So ax equals 1719, 3 times 5 divided by 1031.4. Okay, now I need to find ay, and I can find ay by summing about this middle point. And so I'm going to sum moments about B. And I'm going to have negative 1719 times 4/5 times 49 plus ay times 70. All of that equals 0. So I can find that ay equals, so we have 1719.8 times 49 times divide by 70, and I get 962.64. So now I need to square the ax, square the ay. So we've squared, swap, squared, add them together, take the square root, and I'm going to get that my reaction resultant at A is 1410.837, whatever my units are, pounds. Okay, and as a whole number, so I'm going to have 1411. That's going to be the actual shear force that's acting on that pin. MOE for the material. Well, that's going to be my modulus of elasticity, which MOE is E, which is the slope of the elastic region. So here we go. I just need any point. Here's my elastic region. And I don't want to use this one because I can't even see those numbers. So I'm going to use the lower because it shows me that elastic region. And here's a nice point that crosses. So I have a 60, and then I have to look at the bottom number. And I can't read that, but I think it says 0.002. So slope is E is rise over run is 60 KSI over 0.002 inch per inch. So my E is 30,000 KSI. Okay. What is yield stress? Okay, yield stress is, gosh, that's where we begin yielding. And it's kind of like right in here. So 90 to that, so 105. For a bar with a cross-sectional area of 9.5 inches squared, what is the strain? Strain is change in length over original length. If a tensile stress, so my stress is 78 KSI, and has a modulus of elasticity of 10,223 KSI, assume linear elastic. That's perfect, except I can't spell. So what am I trying to find? What is the strain? Okay, well, stress is P over A, and that was already given to me. Stress, I know that stress equals E times strain. I have a stress of 78 KSI, 10,223 strain. So I can just divide 78 divided by 10,223 divided by, and I get a strain of 12.0076. Enter to the 10,000ths place. There's my strain. Okay, determine the shear strain given P equals 1433 My length is 1.9, so that's 19. 15.2. The depth of the block is 9.9, so if I could look in the back, like make it 3D. Okay, and I'm pulling across the top. 9.9 inches. The shear modulus G is 639 psi, and I want to find the shear strain. So shear strain is gamma. Okay, I don't know if you can see that, gamma. That's what I want to find. So I know that shear strain comes from shear stress, and I have G, that's given. I'm trying to find this, I don't know, shear stress. So stress is V over A. It's just like P over A. Okay, as I'm pulling here on the top at 1433, that is creating across the top of this. It's now parallel, it's now shear. So my shear is 1433. Now what area are we shearing across? Well, it's this top area. So the area up here is 9.9 times 19. So I have shear is V over A is 1433 over 9.9 times 19, and I get a shear stress of 1433, enter, 9.9, enter, 19 times, divided by, I get a shear stress of 7.618 psi. Okay, and I'm given a G, so I have shear equals G, so I have 7.618 psi equals 639 psi times shear strain. So shear strain is 7.618 divided by 639, and I get 1.192 times 10 to the negative 2, so that is 0.0119, and I want this to 4 figures to the right, 1, 2, 3, 4, and in radians, well, that's what I'm working with, is radians, that's the units, so the answer to this is 0.0119. Now, if I know that, 0.1009, and I know this height, I could actually go back and figure out the delta. But I didn't ask for the delta. We were just looking at finding gamma. And are there any more questions? Nope, that's it.